about the stresses under plastic yielding. Let's briefly talk about the strains. So again, returning to our tensile test. So this is a uniaxial stress test, so there's only one stress. And we're going to assume that the material behaves in a perfectly plastic way, so that the sigma 1,1 stress at some point begins to yield. All right, and here we're going to assume that the strain in the 1,1 direction is the boundary condition. So, it's some fixed value. Say we're going to run this experiment to 20% strain. So this would just be a standard displacement controlled type test. Okay. So if we write down what the elastic strains are via Hooke's law, we have this equation, but of course there's only one stress, so these two terms are zero. So we have that sigma 1,1 over E. And right at the point of yielding, then we have Y over E, right? So in this plastic regime. So same thing, sigma 2,2 is minus mu over E sigma 1,1, which is equal to minus mu Y over E. Sigma 3,3 is equal to minus mu E sigma 1,1 minus mu Y over E. Okay? And if you remember, we had this, that the total strain rate is equal to the elastic strain rate plus the plastic strain rate. Right? We had this assumption that we can additively decompose the strain rate into an elastic part and a plastic part. So the elastic part is essentially given by these equations. We need some equation for the plastic part. And so that equation is called a flow rule. And it's really a constitutive model for the evolution of the plastic strain rate. So we're going to say that the plastic strain rate tensor is equal to lambda dot, which is some undetermined multiplier, some undetermined function at this point, times partial F partial sigma ij, where F is our yield function. So for von Mises, that's square root of 3j2 minus y equals to 0. Right? And geometrically, sigma 1, sigma 2, sigma 3. So here, this is our yield function. This is F, right? This circle. And so geometrically, what is partial F partial sigma ij? It's some vector that's normal to this surface, right? Partial F partial sigma ij. It's some vector normal to that surface. And so what lambda is essentially, if we evaluate the stress and we find ourselves out here, lambda is sort of this penalty parameter, this distance outside the yield surface that we're going to bring ourselves back onto the yield surface with. Okay? So this is the direction, and lambda is sort of the magnitude. We can also write this in an incremental form, like So for this yield surface, you know, I can also write this guy as J2 equal to what? I'm sorry, J2 minus y squared over 3 equal to 0. Everybody see that? Right, I just squared this. I moved the y over here, squared both sides of the equation, and then divided by 3, and then moved it back. So I get this equation. Right? And so if I actually evaluate partial f partial sigma ij, right, that's the same as saying partial sigma ij j2, right? Because this is a constant. This term is a constant, so the derivative with respect to sigma ij is 0. So it's just this, right? Well, what is that? What is this? It was a homework problem, right? It's Sij, right? So that was a homework problem. And I think most of you got it right, so I won't go over. I had it in my notes to derive it, but most of you did it right. And it's also in the posted solution, the full derivation. Okay? So then our flow rule then could be dEp d lambda Sij. Right? Just plugging that in over here. I guess I should mention that this is called an associated flow rule. And that's because it's associated with the yield surface, right? The flow rule is defined as some function of the yield surface. And there are other flow rules, non-associative flow rules, that are not associated with the yield surface. A lot of times these are actually used in soils. But both the mathematical and the physical justification for the non-associative flow rules is really kind of questioned, even though some people use them because they can be made to represent experiments under certain cases. Anyway, we're not going to cover non-associative flow rules. But another point, sometimes you'll see it written like this, and other times you'll see it written possibly like this. So you simply just divide by, so another way you could write this is Sij over the magnitude of Sij, where we've defined the magnitude of a tensor before. The magnitude of a tensor is the square root Sij, Sij. Right? And so this gives you like a direction. And the reason they're the same, or it doesn't really matter which one you use, is again, this is a direction, and lambda is this penalty parameter. It's some unknown function we're going to solve for. And so it doesn't really matter. I mean, ultimately we're going to solve for it, and so it doesn't really matter if we include, this is a tensor that has a magnitude. This is a tensor that doesn't, right? It's a unit tensor. You might call this thing like Qij. So it's a unit tensor. It doesn't have magnitude. But ultimately, we're going to solve for this unknown function, and it doesn't matter how we defined it. Either that magnitude will be included in the solution of lambda or it won't, right? And because this is just a penalty parameter, it's something we're going to solve for and then eliminate from the equations. And so it doesn't matter if you include it or not, right? I just wanted to show you that these are really one and the same, and you may see it written, associated flow rule written in either way. So if we sort of return to the problem, now we have this d lambda dp, and now it was Sij, right? So if we compute Sij under those circumstances, we did it last time. You can just look back in your notes. Then you get something that looks like this. Right? And so that means that this term is equal to well, one other point. In this case, in the case of perfect plasticity, and the incremental change of lambda is a constant, because essentially as I move along the yield surface doesn't change in size in any way. So if I were going, later on we'll learn about, say, isotropic hardening. In the case of isotropic hardening, the yield surface actually gets bigger as you strain it. But in this case, the yield surface doesn't get bigger, so the change in lambda with respect to strain, an increment of strain. So if I continue to strain it, there's no change in lambda. So this is just a constant out here. Or you can think of it like 1. And so then with that, you can see that these terms along the diagonal are, so this is the 1,1 component of the plastic strain. This is the 1,1 component of the plastic strain divided by 2. This is the 1,1 component of the plastic strain divided by 2. And so then there we have our strains defined. So if we return to the equations, we had that sigma 1,1 is equal to y over E plus sigma 1,1p. Therefore, sigma 1,1p is equal to sigma 1,1 minus y over E. Okay, so we just solve for that equation. And remember, sigma 1,1, I keep saying sigma, epsilon 1,1 was a boundary condition. So we have like 20% strain or something. So therefore, we can fully define what the plastic strain would be by just plugging that into that equation. And likewise for sigma 3,3. So these are what the strains are in the uniaxial tension tests for a model that has perfect plasticity. But I don't know. I had this in my notes because I did it last year, and I don't really know how useful it is. Let's move on to something useful. It's sort of a it's the one case where you can kind of write down the full strains, but it's not of that much interest in a computation or for real materials. Right? So that's in a one-dimensional case.